Hi, I'm Lowell Gustafson, and on behalf of the International Big History Association, I am delighted to welcome you to this webinar on Is There Structure in Big History Dynamics and What Might It Mean to Us, being offered today by Dave LePoire from the Argonne National Laboratory. We appreciate your being here. And in many ways, we think that this represents the central values that Big History stands for, which includes being scholarly and being accessible. Our members and our donors are committed to making Big History as accessible as is possible to everyone. We think it does have great meaning for all of us in all kinds of different ways, which Dave will bring out in his presentation. We invite you, if you're not already a member, to please join with us in the mission that we have here. You'll see that not only will Dave address the central question about is there structure in big history dynamics, but he also asks a series of questions to guide future and big history for the future. So he's giving us the current results of his own research on this question, and he is offering us suggestions for how to pursue future research, both of which are very exciting for us. So with no further ado, let me hand the mic over to Dave LePoire, and again, thank you for joining us for this webinar.
And how they changed, and the structure within each of them, especially in time and energy. And so I kind of work in the environmental area, also been involved in physics and energy projects, and also in computing science. But I just want to have a little bit of a story. This summer, I got a little bored, so I signed up for a science and comedy course. And I thought it was going to be like about the theory of comedy and discussions like that. But no, it turned out that we had to develop our own 5-minute routine on our experiences in science and make it funny. And then I was told that we would not have any slides. So we had to get up there. And then I thought, oh, good, this will be virtual, so I'll be able to do that. And in the last week of that course, they found out Chicago was finally opening. And so, no, they turned it to a real one. We had to go downtown Chicago, in front of a live paint audience to give something. And the first 2 times I tried to introduce myself, I absolutely froze. But the third time was the charm. So I think I'm over that introduction now. So hopefully this will go a little bit smoother. I have the slides and it's virtual, so I can have the notes here. So let's go ahead. And so I think we've seen kind of diagrams kind of like this about big history. And, it gives an impression, okay, a lot of things happened long ago. And in this last turn is kind of, what happened in life and some of the fossils that we've seen. But, it really doesn't have much in terms of human evolution, nor anything at all in terms of civilization. And so this is not a good representation, I think, of a lot of the things that we're kind of concerned about. There's also the cosmic calendar. I think Carl Sagan was one to first make that. And so at the very top row, we have the full year in terms of months. We're in October now, which would be oxygen from photosynthesis. And next month there would be more eukaryote cells being developed, more complex cells. And then only in the last few seconds before New Year's would Columbus arrives in America 1 second before midnight. So this is kind of more interesting. It can kind of break things down into various aspects. I find this one to be kind of more kind of dynamic, that it shows the spiral coming out But again, not too much in terms of human evolution or history on this one. And so when we take a look at this, we kind of think, okay, we know quite a bit, and it's just been amazing what people have been able to figure out a lot over the last century, a century and a half or so. But there's still a lot of questions out there, right? Especially at the transitions. For example, what happened during the Big Bang? How likely is it for a planet like Earth to form that's amenable to life? How did life begin? Why did order actually assemble out of this? To a physicist, looking at this, number one, they would say there's no way that life would form from just a bunch of chemicals. And then you'd ask them a little bit more, and they would say, well, there's no way that the universe would actually come about either, because all the matter would annihilate itself. And so physicists would have trouble believing in formation of life, the formation of the universe, and even their own existence. But here we have this evidence that life does exist, at least on one planet. And so then we have to ask, this life existed, but why and how did consciousness evolve? And then not only consciousness, but then technological consciousness and technological civilization. And what is the fate of that civilization? Because, you take a long look at this. I mean, that whole technological civilization just on the edge of this, right? So, how will this continue? Are we just kind of at the cliff here, we fall over if we get too complex, or will this continue in some way also? So those are the type of questions. And so I'll start this with, some basic questions and kind of the contrasting views that some people might have. Then we'll go to looking at specific trends. So just a small part of the questions, and maybe we can find something in these trends that help give us insight into other questions, right? And so we'll look at the large trends, kind of the thing that I showed on the title slide, and look at large scale trends in terms of how this kind of went through time. And then smaller scale, looking at some of the data for civilization, how complex adaptive systems might fit in, some of the transitions, and then we'll figure out how the cosmos fits in, which is quite a bit different than evolution on Earth. And then we'll take that, look at the current situation, find out what might be going on, and then become more speculative as to what might continue past this. And so we'll take a look. This is kind of the outline of what we're going to be doing. So first, I just wanted to take a look at some of the big questions out there. And so the first one is with the Big Bang. Many questions, but interesting, in the last few years, there's been a couple of books that really kind of take a different view of this. There's a very good book by Peter Atkins, Conjuring the Universe, in which he kind of makes the claim, not quite a claim, because he knows that there's a lot to be learned yet, but his question is, what really did happen during the Big Bang? And his answer to that is pretty much nothing, which is kind of a shocking thing. I think that's what he wanted it, but just because of the symmetries, the physics kind of rolls out, and the universe kind of rolls out from that, versus one that focuses on the asymmetry, that is some of the random events and some of the parameters that are involved, why there is matter at all in the universe. So this is, definitely, one of the controversies or discussions going on in, for example, what happened during the Big Bang. And of course, we're learning more and more about that. It'll take a while, I think, to find out. The next one is, after you have the Big Bang, what drives order? Why would this come together in self-assembling patterns? And so one of the big questions there is it through overcoming entropy, right? Entropy would just allow everything kind of be, scattered all about, and thermal-wise not very interesting, or because of entropy. And so Eric Schneider wrote a paper in the mid 1990s, and more recently a book with Dorian Sagan, Into the Cool, in which they try to make the case that it is because of entropy, that is, at least some self-assembling patterns can be formed to cause entropy gradients to be kind of more relaxed, to actually increase the rate of entropy generation by assembling. Versus kind of the longer term look by Stuart Kaufman, The Origins of Order, looking at self-catalyzing chemicals or systems in there, kind of overcoming some of the entropy. So this is actively being discussed and looked into, and no one has the answer to that. Then once we have order, well, how rare is life? And so Peter Ward, used to be with University of Washington, had a book on that, saying that, you know, there's just a lot of the circumstances, the Goldilocks kind of conditions that makes it rather rare. And then others, Alexander Panoff, who also kind of thinks about the panspermia, that, you know, once life developed on one particular location, it can be spread to others. In fact, there are organisms that can survive in space all alone, not in spacecraft. And so that is going to be answered, and there's going to be a lot of discussion about this, especially with discoveries on Venus and Mars and the extra the planets being found outside of our solar system. And so another question is that once life exists, is life in harmony or self-destructive? And James Lovelock has been writing for quite a long time on Gaia hypothesis that the Earth is kind of like a self-regulating system in terms of temperatures and gases in the atmosphere. And life is a part of that. And so he has this daisy world type of model to show something like that. And again, Peter Ward, the one who thinks that, you know, Earth is rare, has the other one. He says life pretty much just, you know, takes all the resources and it kind of causes catastrophes, goes to the limit, and when the resources are insufficient, or if there's very vulnerabilities, they can be destroyed kind of quickly. And so I think it's kind of a mix of these two, but again, this is a type of thing that is being discussed. You can see that James Lovelock even has gone a little bit after writing for decades about Gaia and how nice things are. One of his recent books is The Revenge of Gaia, saying that, okay, be self-regulatory, something might have to be done with these humans that are using these resources. And then we get not only to life, but to humans. And so is consciousness emergent or physical? And of course, this is a big topic being discussed with the advances made in artificial intelligence, in terms of images, self-driving cars, in terms of languages being found and interpreted. And so, you know, what is consciousness? I do not believe that we know this. A lot of people would say differently. You know, how is it evolutionary beneficial? And then the hard question. And I remember when I saw the hard question first, you know, a few years ago, what is red? It seems like a very simple question. But when you think about it, red is just our own construction in our minds. And it's kind of a quality, kind of tied with some consciousness. So what is red is one of the difficult questions, whereas other questions like how do things learn, how do they plan, how do they play games, things like that are, you know, considered to be at least solvable. But what is red is kind of more long-term. And so various discussions going on about that. And then finally, you know, what is the fate of a technological civilization? So are we on a path to some technological kind of utopia, or being able to, you know, free some of the burdens that we have? Ray Kurzweil is the one a number of years ago wrote the singularity is near. And he kind of used this trend in electronics, for example, Moore's law, and that Moore's law is actually speeding up. And so he predicted this technological singularity, whereas Jared Diamond is more in anthropology and travels. We're looking at how people live in ecosystems. And so he's looked at a little bit less optimistic view, some would say pessimistic, and you can find a lot of discussion about potential collapse. And so, hopefully it'll be somewhere, in between these, but hopefully we'll find out relatively soon because things are moving along quite quickly. So in terms of the motivation for myself, I remember reading Carl Sagan's Dragons of Eden book in the late 1970s. And I remember seeing the transitions of information that we'll look at in the next slide, I believe. So that was a big impact. And then Modis came along, I believe in 2002, and had a very bold kind of paper on technological forecasting and social change, in which he plotted, took a lot of people's events through history, including Carl Sagan's and others, and he kind of combined them to become somewhat independent. And he came up with this kind of singularity trend here. And then I've found others kind of with the time scaling of events by Alexander Panoff and Graham Snooks, and then energy as an important driver. And I'm still finding, a lot of different papers kind of in this because this belongs to no one field. And that's what is making it somewhat difficult. And so I think as we bring more and more of this in and together, we can get a better idea instead of all these pieces kind of hanging out there and putting together. I think they can make a very good story. So this is the curve that was in Carl Sagan's 1977 book, Dragons of Eden, and it's very early in the book. And so it has the time from the origin on the Y scale, which is kind of different, and has the number of bits of information on the X scale. So time is going from the top to the bottom. And so life begins early in Earth. And the amount of information in there climbs quite a bit until, somewhat the way that DNA mutations occur becomes a little bit slower. There's a limit to how much information and how fast that information can change. And so that became limited, but another system, the brain or neural system, kind of developed and evolved, and humans made a large impact on that in recent history, as we've seen. And then it just points out, what he calls human extrasomatic cultural information, for example, writing and books and stuff like that. So he has three different information processes, kind of genetic information, DNA, neural system, brain information, and then writing type of thing. So I've kind of broke this down into kind of, life processes with DNA, and then human evolution, kind of the end of this curve with the development of human brains and consciousness. And then later on, they develop civilizations and can spread information much beyond themselves with various writings. So you can see that description over on the left-hand side. So I'll come back to this because I think this is kind of interesting that long ago, this was what people, thought, or at least what Carl Sagan kind of put in with three kind of information phases in history. And there are also early studies of population singularity. The singularity in time is nothing really new. This is a paper by Heinz von Forster, 1960 Science journal, so very reputable one. And so there they predicted doomsday is Friday, November 13th. Of course, it had to be Friday the 13th. in 2026. So we only have about 5 years to go before that. And kind of as he says down here, this is a copy of the actual paper. At this date, the human population will approach infinity. Of course, you have a statement like that, you always want some condition if it grows as it has grown in the last 2 millennia. And so that was correct. But soon after this paper was written, the fractional rate of population growth peaked in the early 1960s, about 2.2%, I believe, and then started to decline. So it was very soon after this paper that, some indications that it wasn't going to go to infinity, and I don't think anybody ever thought it would. But it always has this condition here that the rate, he had it for the last 2 millennia, 2,000 years. And there's been great work by others on this, some independently kind of discovering it, some extending it. And so Andrei Kartev here kind of contributing to it. Kapitsa was a Russian, Kramer, I believe, was from Harvard. And some of these people have extended it further back, claims of, for example, a million years back. Of course, it's tough to do because there was no census of the cavemen, right? They didn't go around with census takers at that time. So it obviously had to be an indirect kind of measurement. And so next slide has this quote on it. So even earlier than that population study in the 1950s, John von Neumann, very instrumental in a lot of the progress in the 20th century. This was kind of related from what he supposedly said by Ulam, one of the kind of developers of nuclear technology. The ever accelerating progress of the technology and changes in the mode of human life gives the appearance of approaching some essential singularity in the history of the race beyond which human affairs as we know them could not continue. So he was even kind of seeing it at the time. So this is kind of an idea that has been out there and discussed by, a lot of different people in a lot of different places. So I just want to give a real quick kind of introduction why the singularity might be easy to see. And so, we have the population studies and we have the event studies, but I think this is one way to kind of summarize it down. When you think about, civilization, human evolution, and life on Earth, think about when those kind of began, right? So those were the three that came from Carl Sagan. So ancient civilization, I have about 5,000 years ago, 3,000 BCE, kind of with Egyptians, Mesopotamia, India, and China type of thing, the civilization started. And so in our history books at school, this is kind of where things would start, about 5,000 years. Well, then you think about when humans kind of started, and not when the human species came about, but when the human line kind of split from the rest of the current apes, right? And so, the human line, there's a lot of, skeletons out there, a lot of different species. And in fact, they kind of split. Some survived, some didn't. But the line split from the current apes about 5 million years ago. So some would have about 6 million years ago with various evidence. You can argue about that. It's somewhere in there. And so I kind of like to round these numbers, 5 million plus or minus 1 million, doesn't really matter. It's kind of a small change. And then Earth formation, continue that. Well, that's about 5 billion years ago. And so a lot of people would say, no, it's 4.54 billion years ago. And Claire Patterson had a lot to do with that measurement. And part of the measurement was done at the lab that I currently work at. And so I'm not dissing those people who put the 4.54. There's a lot of work in doing that. But for this purpose, I'm rounding these numbers, right? And so about 5,000 years ago, ancient civilization, about 5 million years ago, human line splits, about 5 billion years, Earth formation. So you can see this trend, right? They're different by a factor of 1,000. And I put this together, and then I saw in the Dutch Montessori schools that they have a very similar type of split with the factor of 1,000, but I think they have 10,000 years ago, 10 million years ago, and 10 billion years ago, kind of on the age of the universe. So those ideas are definitely out there. But how can you actually see this or visualize this? So I think of, instead of time scales like the calendar, I like to think of spatial scales. And so the Earth formation, if you say it's 1 kilometer, that's about the width of Central Park in New York City. Then if you the human line splits, it's 1/1000th of that, so that's 1 meter. So you can imagine, one person there, and half of the height of that person would represent the human evolution. And then if that person takes out a coin from their pocket, the width of the coin, the dime here, is about 1 millimeter, which would represent ancient civilization. So that's, the width of this. And so, our, everything in the regular history would occur within this width when we're looking at this scale here. So we had Andre and I put together an edited book kind of this, the 21st Century Singularity Global Futures, a big history perspective. And we had, contributions from a lot of people around the world, including many big history members in there. And we looked at, first of all, we had a definition, kind of looking at the trend. And then we would have other people look at possibly how that might continue, but we were kind of focused on the big history in terms of the definition of the trend that was occurring in the past. We had like a diagram very similar to what is in Eric Jant's 1980 book, kind of on the large scale and a small scale. In a paper I wrote previously for Journal Big History, I showed how, taking some very elementary fundamental constants of physics, that you can kind of derive most of the sizes of these objects in big history. So that's there. And then we looked at various things in terms of not only the population, but in science and economics. And looked into what this means kind of for technology. And the Grinnans wrote very much on using cyber technology, nanotechnology, and that whole group of technologies, and maybe applying that to healthcare in the future. But now that we saw, a singularity, now are there any other structures to it? And so this is what I did immediately kind of after reading Modis's paper. I knew of one system that had slowed down, and that is progress in fundamental physics. Because I was thinking of going into that, and it contributed a little bit, but they were beginning to call the future accelerator the Desertron because they didn't think they'd see anything, and they really didn't. They only saw really major discoveries was the Higgs particle, which was even known kind of at that time, and we were working on models of the detector to see it. But so it seems to have slowed down, and the peak rate seemed to be in the 1920s and 30s when amazingly the quantum mechanics nuclear kind of combination was developed along a little bit earlier with the general relativity. And so it took events in the history of physics, grouped them by the subfields, then plotted the progress in each one of those fields, grouped them together to find out, the duration of those discoveries, right? How long did it take to, find out fundamental gravity and classical mechanics? And then, put that on a logistic curve also. So this is a logistic curve of the results of the individual topic logistic curves, right? So there is a nested pattern of transitions, it seems like, in this particular field. And so what I wanted to do is to look at nested parts of the big three transitions. And so one of the easiest ones to take a look at are the kind of the current ones. The hardest one is the human evolution, because a lot of it occurred in the brain, and they used a lot of wood tools, and there's not a whole lot left from that. But here in primitive agricultural transition, it's no one day that they decided to go from hunter-gatherers to farmers. It took a while, and this shows, over 10,000 years of various things. I know Ken Baskin, I had a discussion with him recently, and he said another good book is Against the Grain, in terms of, looking at this transition, that it seems like people didn't want to take this up just automatically. They were kind of, because it was more work. But we'll take a look at just a little bit here, is that I did put together some simple models of historical transitions, right? So we saw that there was some evidence of a logistic transition in the hunter-gatherer to agricultural, and I kind of make some analogies here, and that is in the agricultural transition, the blue dots kind of correspond to hunter-gatherers. And at first, no one wants to do the farming, right? There's enough land for everybody. So this is kind of a bird's eye view of the land. Then as they grow, they get a little bit crowded, and there might be some events, for example, droughts or whatever, that cause people to want to move to something else. And so they move to farming. And when they move to farming, it's more intensive. It drops the area that they need to support themselves. But this then continues because they have a higher growth rate, and soon will replace kind of most of the hunter-gatherers around there. So this is kind of like a liquid and gas phase transition. And there's a paper in the journal Big History on this with these curves. So I looked at the agriculture of the civilization, where it's kind of a return on scales, and also in terms of insurance. Civilization kind of to more trade and capitalist system, kind of based on a prairie model. Trade industrial kind of looks at the question of why didn't China, with all the innovations, it kind of developed the Industrial Revolution first. And one of the things is that, well, Europe was kind of far behind. But then once the trade routes were formed, a lot of those innovations came and hit Europe kind of in the right time to have kind of a self-sustaining innovation rate that kind of led to industrial revolution. And I'll have more on the sustainable rocket launch a little bit later. So this is the cover diagram. So we have nested transitions. So we have these three major evolutionary phases on Earth: life, humans, and civilization. The time scale decreases by a factor of 1,000. And then looking at one of these, we also have about 6 phases here, each one decreasing in time by about a factor of 3. And so you can see that 3 to the 6th power is just about 1,000. Right? And so it's actually the square root of 10, which is like 3.16, something like that. So I just rounded it to 3. There seems to be, some energy transitions, at the splitting. And I said, that we've already seen one system that had nested transition, that is in physics development. And so I'm kind of in working on the time scale and energy transitions. What's kind of nice about this, just to think about it, is that pretty much the times kind of change by a factor of 3 in here. And so can kind of easily go through that and kind of remember what kind of some of the major events in the evolution. So this is what the 3 phases would look like in real time, right? So you have the beginning of the Earth up the top here. and then evolution of the Earth and evolution of life, and then the change to a more complex cell, oxygen generation, which I think is where October was, and then 1/1000th of that is where humans develop through hominids, speech and fire, kind of down below, and then 1/1000th of that would be the history that kind of we know. So what would this look like in log scale? And this is what I like to see. Okay, this kind of makes sense, right? And I know people use log scale on this quite a bit. For example, on a big history projects. But here you see that I have the main evolutions on Earth, life, human, and civilization, starting about 5 billion, 5 million, and 5,000 years ago. And there's factors of 3 in there, so about 6 subphases, transitions in there. The singularity would occur kind of at the end, but it seems to be transitioning now. People debate that. But then the whole early, before Earth formed, it's just another factor of 3, right? From 5 to 15 billion years ago. And so this cosmic phase is definitely quite a bit different than this evolution on Earth. And so we can see complex adaptive systems evolve by learning, and some of that learning also causes them to grow and to use resources to go towards limits on the environment, which means they're going to have to solve some additional problems, right? And so that's the idea that some system tends to grow kind of normally to fill the environment. It reaches the limits, then there's a decision point where, for example, it has to go to farming to reduce to make it more intensive, and then they can grow again until another kind of crisis point comes up. For example, the need to kind of organize things in civilizations. And so one of the main things is that energy seems to be the driver of this, or the energy flow rate. And so where does the Big Bang fit into the scales? Well, it's be 3 times the age of the universe is about 3 times that of Earth, so it's almost the length of Central Park in New York City. So what can we say about this cosmic phase? Well, it has its own time scale, right? Things happen quickly, right? There was the book, Steven Weinberg in the late 1970s, again, the first 3 minutes, where a lot of things happen in the first 3 minutes. And then, things kind of clump together. And so this turning point would be where Earth forms. And then the evolution on Earth seems to be trending towards more complex systems, or at least the leading edge of the evolution. And so someone shows this with some type of spiral being faster and faster as it goes there. And so there are 2 different ways of looking at this. The first one we've taken a look at already. You can look from now and look backwards. And so you can see 5,000 years, 5 million years, and 5 billion years. So this situation is not going to stay that way, right? In a million years, everything's going to shift a million years, and it's not going to look like this kind of fractal kind of behavior, right? So it's kind of now is somewhat of a special time when you look at this. From the Big Bang, if you start at the Planck time, the smallest time that you can have, and go to the time now, there's 60 orders of magnitude, and there seems to be something happening somewhat around by a factor of 1 million. And that would, in terms of energy, that be a factor of 1,000 in energy, kind of separating these things. And so even now we know, the universe has cooled. It's cooled to 3K, the background radiation, and our temperature is about 300K. So 1/100th of kind of the normal temperature. If the background radiation was, a lot warmer as it was in the past, well, then things would not be able to form as well. They'd be broken apart by that thermal energy. So what are some possible extensions of this? So I show, that summary of that last curve here. The Big Bang happened, it cooled, Earth formed, then evolution of life and humans and civilization kind of sped things up. And we're kind of going towards a point of maybe inflection or the singularity point. I like to look at it as somewhat of a logistic curve, but others have argued that this is just going to really become a singularity. Others are going to say, things are happening so quickly that we're just going to go into chaos and collapse. And so this is very speculative of what happens in the future from this, right? And so here I show, kind of one way, well, it's just a reflection of the past. The logistic curve kind of continues. And so there was some math in that because it's not really the typical logistic curve. It's a log time logistic curve. And then there's, what's going to happen at this transition to sustainability here. And so I make the analogy to a rocket taking off to our transition from an agricultural society that happened before that was somewhat sustainable, right? We got a hold of oil and it didn't become sustainable, but it really sped up technology. And now we're kind of weaning ourselves off of fossil fuel, hopefully to have some type of advanced sustainable society where we get energy from things other than fossil fuels. Just like the rocket on the launch pad, well, it's stable, but it has a certain amount of fuel. At the end, it's in orbit. It doesn't need any fuel to continue its motion. But in between that transition, that's where it uses that finite amount of fuel to get up there. So there's a lot of analogies I made to that. But in terms of the possible outcomes, both of them have, crash, run out of fuel, overshoot, or go to something sustainable, right? So I kind of see us now as, in this rocket phase, we've already launched and we've not gotten into orbit. And so it's a real question whether, we're going to make it successfully into orbit or overshoot or go in some other direction. So the things that I'm kind of currently working on or have worked on in recent past is, why is this? And so the singularity, there's a very simple math model for it. What is the factor of 1,000? What determines the factor of 3? So there's some ideas that I'm thinking about for that. One is what happens if the limits come earlier? For example, what if there were no fossil fuels to kind of accelerate that technology? Would we just kind of slow down at that time, or would the technologies that we have be developed? What other physical systems might have similar behavior? One of them I found was a coin that is spun goes to a singularity in frequency as it slows down. But the physics of that is extremely more complicated than the simple model that we have that seems to fit a lot of the, at least population data and the event data. And so there's other things there, where do the 18 steps kind of come from? And that led to a question is, what human lifetime does the universe give us? So I kind of went through that. This is published in Evolution by the Russians with Leonid Grinin's publishing press. And so the two main places to publish things like this, the journal Big History and the series in Russia, for example, to Evolution, they have a number of working titles in there. So just going to go through the summary. We have the main evolutionary stages, life, human, and civilization. We saw that was based on information processing, kind of through Carl Sagan. There's a factor of 1,000 and kind of could see the singularity trend very easy with the 555, 5 billion, 5 million, 5,000. And then kind of fit in the other events in between, had a factor of 3. So we saw that it was a nested logistic stages with some energy transitions, some historical evidence in terms of event rates, and then some simple models of historical transitions to kind of think about it. We saw that the cosmic phase is kind of a reversal of the time perspective, right? Things slowed down from the beginning, and kind of the two are connected, kind of where Earth forms or some habitable planet for others. So possible extinctions are indications of the inflections, the transition to sustainability, potential reflection, or the other scenarios, which are continuing on technological acceleration or coming to collapse, and many scenarios in between. So I just wanted to show this, the further material and contact information. I'd really like it, to hear some feedback. I have a book that I self-published, but you can, download it for free either by emailing me, davidlepore@gmail.com, or you can go to my ResearchGate page. So just search for ResearchGate LePoire, and you can search for it there, or you can go to specifically to my big history projects in there. I've got one of the chapters from the other book, Exploring the Singularity Concept Within Big History, is also there. And these are some of the Journal of Big History papers that I wrote that kind of talked about in there. So I think that there's just other papers in there, but I think that is it. Thank you very much for listening. And I really would like to hear any feedback or anybody who wants to discuss various things. davidlepore@gmail.com, and we can find out what to do. We're trying to form a research group soon, hopefully meeting maybe sometime next month, kind of to talk about these type of issues and things that are in the Journal of Big History. So I really appreciate, if you send me an email or let somebody know that you're interested in that research group. Otherwise, thank you very much, and I would appreciate any questions or comments now also.
Well, thank you so much, David, for this really wonderful presentation. It's a great talk. I see a number of questions in the chats. Why don't I start by asking if anyone wishes to unmute themselves and ask David a question directly? And if you don't jump in, I will. So please, someone do that.
A quick question, David. You ask, at what point did consciousness evolve? I don't know if you're familiar with the work of Amit Goswami, is a theoretical quantum physicist. At one point, he had the textbook on theoretical quantum physics. And he says that the only way to resolve the quantum measurement problem is to assume that consciousness comes first and matter comes later. I was wondering if you'd built that into your thoughts at all.
Yeah, I'm not familiar with that book. Thanks for mentioning that. I've seen other discussions kind of on that. Stuart Hameroff had Paulo Pizzi. I don't know if that's the name, but she kind of said consciousness started with the Big Bang type of thing. And there's a lot of people that see possibilities and are still kind of talking about it, right? I mean, there's a huge range of possibilities. I think with the humans, I think it went up a scale, mostly because of theory of mind, being able to kind of, recursive ability to kind of have a model of what's in other people's minds, and including their model of other people, right? And so something happened there, but you're right that consciousness, various measures of it, people have looked at in, non-human subjects. Very good, thank you.
I see hands up from Max Barnett and Emlyn Costa. Max, could I turn to you first and ask your question?
Yeah, thanks a lot, David. I really enjoyed it, as always. I really wanted to ask you about it's the kind of expanding and contracting of complexity within the kind of nested transitions.
Yes.
Because I think, we perhaps sometimes get trapped in big history when we're talking about this kind of narrative of increasing complexity all the time. But I think within each nested transition, there is always a great deal of fluctuation and a lot of kind of points at which, you know, that innovation might not happen fast enough. I mean, I obviously come from the human society side of things a bit more. But yeah, I was wondering if you could talk to that a little bit more in terms of how we build, I guess, the cyclical nature of complexity into our modeling.
How we build, I'm sorry, how we build a,
The kind of cyclical nature of complexity into our modeling.
yeah, so obviously in evolution, you know, people said, you know, evolution goal, you know, the goal was not consciousness or brain or complexity, but you know, we're just kind of looking at the leading edge of it, and so it's usually, you know, a system that you know, finds some environment in there, grows, and eventually it will hit
Hey,
some
Matt, how
limit.
you doing?
It will hit some limit, and then from there,
No, this is Ken. You
you
got
know, it
my
has a
landline number.
capability to, you know, either stagnate there or kind of, you know, solve a problem. And so it's kind of the stressed systems that, you know, that are going to be the ones kind of continuing in complexity. And there was, you know, in terms of ecosystems, you know, people have models of, you know, ecosystems becoming more complex, and then at some point they hit the limits, and those you know, bifurcations actually reverse, right? And so it kind of comes back together, and not too much has been written on that too recently. I don't know if that helps or
Yeah, absolutely.
addresses that.
Yeah.
Good.
Thanks a lot.
Good. If I could turn to Emlyn and then Tyler Volk, please. Emlyn?
Yeah, thanks, Lowell, and hello, David. The story that you've been, or the account that you've presented to us, is one of entirely the sequence of natural process results. I would like to sort of add to the picture and ask your comment on where we are geologically now. And I want to just quote, last week I attended the second plenary conference of the International Science Council and probed what it has said about the Anthropocene. The Science Council, as we all may know, is the new amalgam of the natural and social sciences worldwide. And in the Human Development Report called The Next Frontier, it says, and I quote, and I put this in the chat, for the first time in a relationship spanning 300,000 years, instead of the planet shaping humans, humans are shaping the planet. And this is the Anthropocene, the age of humans, which is my focus these days from a museological and geological standpoint. So where does the Anthropocene and this new non-natural, i.e. human, which we should think of natural, but it's not, how have Homo sapiens altered the trajectory of your sort of sequence of natural processes?
Yeah, so you know, from the you know, early parts of humans, I mean, one of the kind of like to say is that you know, humans specialized in being general type of organisms, right? We don't have claws, we can't run all that fast, but their ability to move and explore new areas and new environments was, you know, seen in their migrations. Currently, what I see is, I mean, it's a very good question, is that, you know, this is the limit, that the environment is part of the limit that we're seeing. And it's a question whether, you know, we can organize to move beyond this limit, or will it kind of, you know, get us before we solve this issue. So, I know I saw a paper kind of writing on this. They were looking at other, you know, possible, you know, civilizations out there and asking whether they would have at some point a climate kind of catastrophe or climate crisis, I guess was what it was. and their answer was, kind of yes, it was very probable. I had a lot of questions on it, but I think it's just very interesting. And so this is one of the questions that I'm looking at is, this is a very strange time. We were using all this fossil fuel that kind of came from very early Earth in a special condition when, wood was being produced. And so the cell structure, but there was nothing really to decompose it. And so it kind of built up. And that's not necessarily what would happen on all planets, I don't think. It was just a small part of it that was converted to oil. So right now we're using that from so long ago. My questions there are, what would happen if the oil was not there? And now we're taking that carbon, from that buildup, and that was part of Earth's evolution to store that carbon so there'd be more oxygen in the air. And so now we're putting that back into the air, kind of reversing that process. So I think very integral in terms of what are the limits of the Earth. Been following the Rockström's planetary boundaries, where listed 9 or 11 or how many boundaries people argue for more or less, but they're there, and I tried to get involved with that, and I have not been. I'm in an environmental science group where a lot of people kind of look at some of these issues. Did that address your questions?
Well, yeah, you're touching on it. I think it's. I don't want to take more time. I would otherwise have supplementaries, but thank you for commenting as you do.
Thank you.
Thank you. And again, I see hands up. If I could first turn to Tyler Volk and then to Matthew Chandran Kunal. Tyler?
Yes. Okay. I'm on now. I should be on now. Okay, David, thank you. So I just want to go into a bit your factor of 1,000, the 3 periods, and to maybe ask you how defensible you think that is in terms of defining those periods. Because I have preferred in some of the writings I've done to look at the large scale events as different evolutionary processes. So biological evolution, and when cultural evolution started, you get a new kind of dynamics forming to create forms. So I guess the one I would have the most issue with, the question would be the 5 million year one. Now, because then that goes in the middle, right, between your 5 billion and your 5,000, which is so the origin of writing, let's say 5,000 civilization. But the 5 million would be the splitting off of the human lineage from the ape lineage, but the humans were not really human at that point. The brain didn't really start growing until Homo erectus, which is several million years after that. And then it's also been a mystery why the early stone tools developed so slowly over such a long period of time. So a lot of people really put the emphasis on the transition in which culture and language get into gear would be the middle Paleolithic or the upper Paleolithic. Some debates going on around there. So we're talking 200,000 years, 100,000 years, maybe even less than 100,000 years for cultural evolution to really get going, and probably more acceptance of English. So to you, that would just be one of your 6. So I'm wondering why, it seems like you built a lot from Sagan's data, and I'm just wondering how scientifically defensible that is going to be what kind of metric you're going to really use to do this 3 factor of 1,000. 3 times.
I mean, you have very good points and questions in there, so I based on the information changes in there, but I looked into that curve that Sagan had, and there's been a lot of progress on various parts of that since the late 1970s. And I'm not sure that that curve would necessarily stand up right now. I mean, there is a progress in terms of the information, but there's just much being learned in terms of
Right.
the DNA, how much of DNA is used versus being there, and what goes on in the human mind in terms of the processing capability.
So yeah,
So-
Dragons of Eden did have a big influence on me too, I have to say. So thanks for bringing it up. But why? But what happened at 5 million years in terms of information? I don't see that it's that different from earlier mammals or earlier primates.
Yeah, so it was kind of the start of the separation, just like Earth was the kind of the start of that process.
Right, but it's genetic. It's not information at that point, because the brain, Lucy, Australopithecus, had the brain the size of a chimpanzee. So I don't really see it defensible that there was a major information break at 5 million years. I got to be honest with you. I don't see that is defensible.
Yeah, this is one of the main points I think that I wanted to take up with this, is that human part, because I realize with yours that it goes kind of from life to culture, and does not have that middle part. And yes, I agree that things are continuing on all the time, right? And so it's very hard to kind of put exact times on these. And so that's why I put about that time, because that's kind of when things kind of separated, whether it's in the mind or being able to kind of due to environmental changes, kind of explore more of the land versus kind of the trees type of thing, or how they hunted various things in terms of for example, scavenging. And so a lot of those things kind of went in there, right, in terms of getting their nutrition and, having the physical ability to put energy more to the brain rather than to the digestive system. So
but that's not what the archaeologists say. It's not 5 million. That they're not saying that. It's
okay.
I don't know. So I just want to I think searching for these patterns, as you know, since I'm into the same thing, very important. Yeah. But I do want to say I don't think the 5 million year number is defensible as a major information change. Or I need to see a lot more quantitative data on that. Okay.
Yep. Very good. Well, thank you very much. I hope we can kind of continue this discussion. I think it's important. Yeah. Very good.
And then Matthew, are you still with us?
Yes, I am. Yes. So thank you, Dave, for this excellent presentation. And it was a very comprehensive history of the whole universe, its beginning. So we can say that it's really pertaining to the big history. And I really liked your diagrams, and also maybe the paintings and all other things. My question is regarding this quantum consciousness. So where you were mentioning about it. So we have now the further developments of quantum mechanics and connecting it with the artificial intelligence or the machine learning, and how fast these two will be merging into have a kind of connectivity with artificial intelligence or quantum consciousness, which will be connecting or maybe launching into a new level, as you were showing that the rocket launching, and then how fast it will be accelerating us to new developments and new transformations in our own consciousness by linking with this artificial. So how do you perceive our future?
That's always a dangerous question to answer. So the various scenarios, and so I don't think anybody really knows, what quantum computing is good for. I mean, the main one right now is communication, right? Secure communication and the ability to kind of hack into other communication that we have now. So that's been, a large focus, but people are, putting a lot in this. And where I work, I mean, they have a quantum computing, institute, like many other places, are taking a look at it. But, I don't think, the question is, well, what good will quantum computing, do? That's the question, everyone's kind of waiting to see once what will actually happen with that. And I think it'll be kind of interesting, at least. We don't know whether, quantum computing is, just going to follow the Moore's law or faster, or, it could follow the model of, nuclear fusion energy, right? Where it's always, 30 to 50 years in the future, no matter how long you go. So that's the huge question mark in there. I know, just a lot of people have kind of been, thinking about this and coming up with very ingenious ways to kind of connect that. But, it's tough because they have, right now they have to have so many bits, quantum bits, to actually have one bit actually mean something, right? A lot of error correction, but they're making good progress. So unless you have ideas, I really don't know.
So it's still uncertain and unpredictable, you think?
Yeah, I think there's a lot to learn and trying things out, and I think making really good progress right now, but who knows?
Thank you. Thank you.
I see hands up from Claudio Maccone and Jesse Henshaw. So Claudio, can I turn it over to you?
Yes, thank you.
So
Thank you very much, David. Really, I share your ideas. I would say nearly 100%. Actually, perhaps I'd be more ambitious or more crazy. This is up to you to decide. But the point was that in my recent book about SETI, evolution and SETI, SETI is the search for extraterrestrial intelligence that I regard as the final stage of human evolution. So anyway, in this book, I have tried to set up a string of mathematical theorems rather than just unconnected topics. This, of course, is difficult and hinges on difficult mathematics of stochastic processes. But since you are a physicist, as I am, we are the kind of guys that enjoy this sort of things. So the point is that these points that you and I raised should be popularized. This is the goal of big history, to make difficult theorems, discoveries, mathematics, whatever, popular to the extent that people can understand them easily by words. So I would be glad to join the research group that you mentioned, and I would be even happier if someone could help me to popularize all these, with your help, of course. Thank you very much.
all right, very good, thank you. Yeah, I think. Go ahead.
No, yours.
Yeah, I was thinking, one of the things to do is try to calculate the probabilities of, moving from, one phase to another, and what kind of limitations are to kind of put it into, Drake's equation. But I think right now we don't have, the capability of doing the modeling of ecosystems or of Earth systems. But I know, people are thinking about it. So hopefully, sometime someone will be able to put it together.
Thank you. Well, let me just mention two of these people that just as they come to my mind. Well, one, of course, is Andrei Korotayev from Russia, versant with mathematics, and he follows up the theory of stochastic processes that I've been using in my book. And the other ones are the people from his group. First of all, Alexander Panov, who is an old friend of mine, who has been playing a key role in Russian SETI, the Russian search for extraterrestrial intelligence. So it's not just a matter of working together with Big History, but also with SETI. And the other one is, of course, the group of people from the Russian group itself. There is one more point that I would like to mention, and then perhaps we can follow up later. The cumulative learning that you mentioned with an equation that you gave, and I read it, the first derivatives equals a constant time the function squared, is actually what physicists call the equation. You may know about that. It is widely used in control theory, but it is not solvable exactly if you have the full equation. Paradoxically, it is solvable only if the known terms is taken away. So anyway, if you like, in the future, we can talk more about cumulative learning and the Riccati equation. Thank you.
All right, thank you.
Thank you. I think both David's list of questions that he began his presentation with and Claudio's comments shows what exciting research we've got to look forward to here in the future. But for now, Jesse, let me turn the mic over to you.
Yeah, hi. My internet connection's a little unstable, so that's why I've been popping in and out. It's a wonderful exploration, I must say, and very tantalizing. I've been studying the nature of S-curves in the world for many years, and I took a field study approach to learning about them, and quickly noticed that all complex systems seem to begin with a locally emerging period of compound growth, local big bang of positive environmental feedback. And so that let me study their organizational processes as structural developments. And I wonder what you think about perhaps a method of locating milestones in terms of the signs of the feedbacks, because an S-curve starts with a positive feedback trend and then switches in the middle to a negative feedback, going from beginning the development to finishing the development. And so you can divide it into three parts that way, or three events that way. And then if you take the derivative, each of those, the initial processes has a beginning and ending too. So you get 4, and then if you do it again, you get 8 feedback reversals on the curve. And that would give you a way to use richer data rather than simply our intuitive sense of what the big changes were.
Yeah, very good. I have not thought of it in that way, and I think that might be a good way of going, because like I had the event rate data, and that doesn't apply to all those transitions, right? All those transitions don't have it, including the human one, right? And so I think looking for the positive and negative feedbacks, I think would be good. And so negative feedbacks kind of would be where a limit is being approached.
Right.
And so we can find that, and positive feedback is where kind of they're entering a new environmental niche kind of, and so they can exploit those resources quickly. So I think, separating it like that might, give access to more information and data, like you said. Very good.
Yeah, I put my the recent paper I wrote on it and my talk about the paper in the chat for anyone who wants to save the chat. And I just to mention one other thing, I visualize it as the switch from positive feedback to negative as a transition from having a baseline of the floor and multiplying your departure from the floor, and then switching to dividing your distance to the ceiling. And so switching the baseline of the curve from floor to ceiling.
Well, thank you, Jesse. Ken, can I turn the mic over to you at this point?
Sure. Yeah, I have to agree with Jesse that, to back up a little bit, I think David and others have thought that maybe complexity is driven by our universe's quest to have thermal equilibrium. So whatever drives that quicker is what's favored, at least to persist. But I wonder if we look more in depth at milestones, and that's what I'm kind of interested in, is looking more in depth these various milestones, if sometimes it isn't actually driven by feedback mechanisms rather than thermal equilibrium drives. For example, when suns and galaxies formed, it was the positive feedback of gravity probably that drove that process to a greater extent. And also looking at other aspects of milestones. I know we're looking for, this was seemed to be a lecture on patterns, which I'm very interested in. Of course, mathematics is nothing more than the precise articulation of patterns, and finding that precision is desirable but not always attainable. But anyway, I think it's really cool that you look at different milestones, but in greater depth, because sometimes things might also be driven by heat sinks or the lack thereof. And that's one of the fundamental problems of our current conundrum with the environment, is that our heat sink is Earth, and it can only handle so much. If we can drive the heat sink to big space, as another example, now we got an infinite heat sink. Anyway, I just think if we look, my main point is I think looking at milestones more in depth from various angles to see why that occurred, we might even find out more sophisticated patterns as well as what you've nicely done today. Would you agree?
Yeah, I think that's a very nice summary of it. There's a lot of work to be done, finding out, characterizing these transitions, seeing what data we can kind of come up with. I think with, human evolution, that's where obviously, it's not as much, but I think with the investigation into artificial intelligence, we'll get a better understanding of the human mind and kind of what phases it had to go through to evolve. But a lot of work to be done. And, as you kind of said, a lot of it might be out there in different, fields of study, right? And finding those and kind of integrating those with, what we have is kind of a huge undertaking. Very good. Thank you.
I think I'll start to maybe intervene and say let's maybe be open to another question or two. But we've been working David pretty hard for a while. But for now, let me turn the mic over, if I could, to Carl Johan Kallemann.
Thank you. Great presentation. I just wanted to comment. I also reacted like a previous commentator at your age of human beings being 5 million years. And, traditionally, I think that what is meant to signify human beings is the fact that they are able to make tools. And that line goes with Homo habilis, which has been dated approximately to 2 million years, 2.1 million years. Now, what I also want to return to is what Ken Baskin brought up earlier, that maybe consciousness is primary to matter. And I think that's a very important philosophical question that anybody dealing with this question will have to attend to. And if you look upon it, that particular shift, that humans were able to make tools, which differentiate them from all other animals that sometimes use tools, then you can look at that as a shift in consciousness. It may not be by itself a something that changes the information flow or something like that, but a shift in consciousness. And I think it's possible to make a case that all of these evolutionary processes ultimately can be understood in terms of such shifts in consciousness. That's just the comment I'd like to make.
Yeah, very good. I think, some brain structures might have to change in terms of making tools as opposed to using them, and also passing on that information to others as to how to make it. So kind of the teaching of that to maintain that cumulative knowledge. So that is the information of how to make tools and what resources you need and what the tools are going to be, used for. And then also the succession of who has that information, because that's going to be, you want to keep that. So very good. Thank you very much.
Thank you.
And I don't want to cut this off before or be premature about that, but let's think about doing that. But I do want to turn the mic over to Ken Baskin for one of our last questions.
A couple of quick ideas. First of all, I love your stuff, David, but I'm a little uncomfortable with the feeling that your basis is materialism. And part of that is the problem that we don't really know what matter is. That, in fact, I have a friend who says that it seems entirely possible that consciousness is one of the enfolded dimensions in string theory. The other thing that would be interesting to get into more is information. I think the proliferation of information right from the Big Bang is one of the main things that has driven evolution toward higher and higher complexity. It's a long conversation, but that's another issue you may want to build into your theory.
Yeah, I think you're right that information is definitely, a part of it, because agents have to build some type of model of their environment, and they need to collect the information and record, results of previous experiences so that they can make that better model. So I know that there's, a lot of kind of discussion on that. And, maybe, there's obviously quite a bit to learn yet. So, I know that a lot of people, we don't know what, a huge percentage of the universe is, and we don't even know kind of why we exist kind of in terms, the matter should have just annihilated each other. So there's a lot to learn. And so, I've been kind of following this quantum consciousness kind of discussion, kind of came from, or my aspect was from Roger Penrose, the physicist. And I know that that's been discussed and debated. But I think there's, a lot of things to learn yet about that and how the information is connected to those systems that adapt. Very good.
I think I see a hand up from Max Barnett. Let's make Max's question the last one. I will take advantage of giving a final, comment. But Max, did you have your hand up?
No, I think I may have done that accidentally wrong.
Okay. Well, then I'll interrupt and just make a final comment and say many, many thanks to David and to all of you. I think this achieves an aspiration of the International Big History Association, which to have this level of conversation and presentation is really satisfying. So thank you to everyone here. Obviously, most of all to David LePoire for starting us off on such an excellent conversation afterwards. And we look forward to future conversations and the research agenda that David and Claudio and others have been laying out for us. This is an exciting field because there are so many unanswered questions yet. So thank you all for being here. We sure appreciate it. And David, I guess any final concluding words that you have?
No, just to thank you very much for organizing this, Lowell, and thank all the participants. Really good questions. The questions are what kind of motivates me to kind of look deeper and the challenges and new ideas. So I really appreciated the questions and discussion afterwards. Thank you.
Okay, thank you all.
Thanks, David.
Thanks, Lowell, David.
See you later. Bye, everyone.
Thank you.
Bye-bye now.